Hey there, APKL class. We're going to take a look at lesson 2.7a, which deals with linear approximations. So it says, look carefully at the figure to the left. What do you see? And if you don't look too closely, it basically looks like it's a circle. However, if you look a little closer, you might notice that there are actually little line segments, and there's actually 24 line segments, making it a 24-sided regular polygon. And I'm not going to pronounce that, but it says when the number of sides becomes this large, very large like that, the length of the sides become smaller, obviously. The calculus definition of a circle is simply a polygon whose number of sides approach, well, if we think of it in this way, kind of like a limit, is the limit of the number of sides approaches, an infinitely large number. So we'd say as the number of sides approaches infinity, then that would mean that the lengths of each of those sides would approach 0, right? And then we get that a smooth curve giving us, just the arc look, and it would give us an actual circle. It says the above phenomenon occurs quite a bit in real life. Examine the guardrails on the side of a curving road. You'll see that they do not match the curve of the road exactly, but they're straight segments of metal that are just shortened pieces to approximate the curve of the road. Similarly, with some of the older roller coasters, you maybe notice they're kind of bumpy like that because they use shorter, straighter pieces to approximate the curves as you go around, because it's apparently less expensive to build them that way than the curved rails. Obviously that gives you a smoother ride, but those would be more expensive. So some of those older ones, those older wooden roller coasters, that's why they're so much bumpier when you ride on those ones. Okay, so basically what we're doing here is we're going to find some equations of tangent lines, which we've been doing throughout this course. But then what we're going to do is we're going to use that tangent line, and we're going to compare a function value that's on the tangent line versus the actual function value on the curve that we're making the tangent line to. Okay, so we're going to approximate values near this this point of tangency on the curve. Okay, and then we're going to kind of examine, well, how far away can we get, what x values can we put in there so that we're within a certain range of, errors and things like that. Okay, so let's read. Suppose we have a function f of x and its tangent line is drawn at the point a f of a shown at the figure at the right. So there's our a f of a right there. The equation of the tangent line, which we'll call L of x, so they're using L of x just instead of y. They're saying it's a line, so we're going to call it a function L of x. It's given by this equation. Now, they make it look harder than, it's really just a linear equation. So if you think of it, it's like y minus y sub 1 equals slope times x minus x sub 1, but we're not using those same variables, but it's the same idea. Like f prime of a, that's the slope of the line at that a value right there, right? So that's like your m, that'll be your slope. We're just calling the function L of x instead of y, so y. And then f of a is the y coordinate at that point, so that's just going to be a number you put in there. So, your f of a and your a are just numbers that are going in there, and also the f prime of a is going to be the slope, so those will be numbers we plug in. And so what else is new is just they call it L of x instead of y, right? Now, I think they use this more often, where they take the actual y sub 1 or the f of a, this y coordinate, and they add it over to the other side, kind of put it in front. So I think that's the way I'll demonstrate it too. Okay, so near x equals a, the function and the tangent line have nearly the same graph, right? So like if I'm zooming in here, and if you're real close to, they almost blend together, right? The curve and the actual line pretty much blend together. So when you're close to this a value, the curve and then the tangent line are real close to each other, okay? So that's linear approximation, right? So, the smaller this little line segment is around that, you don't have a lot of error in what that curve is, and then you'd be making, new tangent lines as you moved away from that curve every so often. So it says if k were some x value very near a, there would be very little difference in the values of L of k and f of k, is what they're saying. So the point that's on the line versus the point that's on the curve, there would be very little difference in those. In this case, we call the tangent line the linear approximation to the function at x equals a, okay? So this is, it's a good approximation of values when you're close to that a value. That's what they're saying, okay? So in example 1, it says use linear approximation, and the function we have is just the cube root of x at x equals 8 to approximate the cube root of 8.1. So, 8.1 is only a tenth, of a unit to the right of 8. So, what they're saying is, we know that the cube root of 8 is 2, but let's say we were using this tangent line that was drawn here to approximate it. It's going to be slightly different than the actual cube root of 8.1. We're going to be using whatever the value is on the tangent line rather than what's on the curve. But they almost seem like they blend together there, right? But there's going to be a little difference, and something to consider too. A cube root function is something it's concave down, we would say. We're going to spend more time talking about that in the next unit, but it's curving downward. It's increasing, but it's not concave up where it's curving up like this. It's actually kind of curving down while it increases. And so if that's the case, a linear tangent line is actually going to be an over approximation as we move away from A, because that'll always be on top of the curve, because as we move away, we're curving down, so it's kind of moving away from that line. So that's something to think about, because I think they may be asking, is this an overestimate or an underestimate? And that question comes up later on, I know. Okay, so something to think about there. Okay, so what we need to do first is we want to find the equation of the tangent line. So we need to do a few things. We're going to, to get the slope, we want to do the derivative. So let's just do f prime of x. And I would think of this f of x. We can think of it as equals x to the 1/3 like that, right? So if we do the derivative, we're going to have 1/3 x to the negative 2/3, right? And because I have to take 1 away from that, so negative 2/3, and so then I'm going to have 1/3, and now it's a cube root of x squared. That's my derivative is going to be. Now, because I'm doing the tangent line at x equals 8, so then I'm going to do f prime of 8 so that I can get the actual slope for this. So I'd have 1/3 times the cube root of 8 squared. And so if we calculate this out, well, 8 squared is 64, the cube root of 64 is 4, and 4 times 3 is 12. So I'd have 1/12 would be my slope for this tangent line that I'm drawing. Okay, so the L of x, which is my tangent line. Okay, so now the ordered pair, is 8, and it's, the cube root of 8 is 2. So 8, 2, that's going to be like my, if I refer back up here quick, right? So I guess I'm using this form, but so A is the 8, and then the f of A is 2, so those will go in there. My slope that I just found is 1/12, so that's going to go in like that. So I'll have 2, so that's my f of A, plus 1/12, which is my slope, or my f prime of A, and then x minus 8. Okay, so there's the equation of the tangent line. Okay, now it does say use this, you're going to use the linear approximation to approximate the cube root of 8.1, okay? So that's what it's saying. It's just saying, okay, we'll plug it into your tangent line equation, 8.1. Okay, and it should be fairly close to what the actual function value is if I did cube root of 8.1 versus putting it in my linear equation here. They should be close. Okay, so if I were to type this into my calculator, I think I did this. Let's see here. Maybe 1/12. Okay, hold on here. Let me put these numbers in. So 2 plus 1/12 times, I should show what I did here. 8.1 is what I'm putting in for x, right? Okay, so typing this in, I'd have 1/12 times 0.1, because 8.1 minus 8 is 0.1, and then I would add 2 to that, right? So if I were going to do that, that's what I was, 1/12 here, and times 0.1, which is what I'll have right here, and then if I add 2 to that, obviously it'll be 2.083 repeating, right? So this turns out to be 2.083 repeating, okay? And that's my approximation for the cube root of, so that's my approximation for what they're asking me. They're using a linear approximation for that, right? Now, if I wanted to see how close that actually is, I can do the cube root of 8.1. I can say, and I think I'll say 8.1 to the, I can do the 1/3 power, 1 divided by 3, like that, enter, oops. What did I do there? Here. Calculator, okay. Get this out of the way, enter. And so if you look at the actual value here, it's 2.00829, you know, and that makes sense because remember we said the linear approximation is going to be a little bit bigger because the curve actually is concave downward, it's curving downward, so it makes sense so we get something slightly smaller here. So 2.00829,885. Yeah. So the actual value of cube root of 8.1 is like 2.00829,885. That's as many digits as the calculator shows. Okay, so we use the linear approximation right here. We got 2.083 repeating as they showed. Okay, so that's an idea of how we do a linear approximation. All right, next example. It says using a calculator, find the error in using the linear approximation of f of x equals e to the x at x equals 0 to approximate. Okay, so this is going to be a similar question where it's going to, we're going to find the amount of error. So the only difference is if we were asked to find the amount of error here, we would have subtracted this number minus this number and got whatever decimal that would have been our error. But so the process here is going to be the same. So what do we want to do? We want to find, first of all, let's just do our f prime of x. And so we know that the derivative of e to the x is just e to the x. That's pretty easy. And so if we do f prime of, we're doing this at 0. And if I put a 0 in there, e to the 0 is just 1. So we've got that. And so the equation of my tangent line, L of x, would equal 1 plus, and my slope is also 1. And then I'd have x minus 0, right? Because my ordered pair turns out to be 0, 1, right? So I'm at my point, and my slope turned out to be 1 right there. So there's my equation, right? And if I use that, I'm supposed to approximate it, approximate e, or the fourth root of e, which really what that means is we're going to be putting in 1/4 for the x, right? If we're going to do the fourth, that'd be like taking e to the 1/4 power, and so the x that we're going to be putting in here would be 1/4, right? So if we do L of 1/4 like that, 1 plus, and then it would be 1 times 1/4. We can see that this is just going to turn out to be 1 plus 0.25, and so 1.25 is our linear approximation of that, right? And if we actually calculate f of 1/4, which really means e to the 1/4 power, and we type that into our calculator, what we're going to get for that, I'm not going to pull my calculator, we did this once, but that's going to be 1.2840. 1.2840. You can easily type that in your calculator, but it's asking us for the amount of error. So to calculate the amount of error, let's see, we're going to take the linear approximation minus the actual function, because we're using this as our base and saying how off is it from that. So our linear approximation minus our actual function value is this, and so we get an error amount of negative 0.0340. Okay, so that's what they mean by calculate the amount of error. So we find our equation of our tangent line, evaluate it at the point in question, which in this case it's we're looking at e to the 1/4 power, right? Okay, so that's what we had to plug in, was 1/4 for that. Okay, and then comparing that to the actual function value. Okay, and I still have my work on here, but that's okay. We'll kind of talk through this one. Okay, so for this last one, it says for the tangent line to this quadratic equation at x equals 4, to have an error of at most 0.1 when approximating f of 4 plus h, find the range for the values of h. Okay, so they asked this in kind of a weird way, but we're going to start this process in the same way. F prime of x, derivative here, 2x minus 3, and then at x equals 4, so when we do f prime of 4, plugging the 4 in there, 8 minus 3 is 5. Okay, so my slope is 5. When I would do up here, my point would actually be 4, 9 if I plug that 4 into my f of x equation. So I've got a 4, 9 for the point, and a slope is going to be 5 is what we got there. So with that information, we've got 9, and then 5 times x minus 4. There's my tangent line equation. Okay, now we want an error of at most 0.1, okay? So in other words, the difference between the tangent line and the function, we want it to be less than or equal to 0.1. Now I put negative here just because I know when I take the tangent line minus the function value, because this is a quadratic equation that's curving up, and so the actual function value is going to be greater than the linear approximation. So I know I'm going to get a negative value there. So when I subtract in that order, I just had negative because I know that difference will be negative. Okay, so here's the way I'm going to do this. This is obviously we're going to need our calculator to figure this out. But so my tangent line, which was this, 9 plus 5 times x minus 4 right there. And so the difference between that and the function, which is my original function here, x squared minus 3x plus 5, I want that difference to be less than that 0.1. Okay, so to do that, I'm going to pull open. I've got it entered into Desmos. We'll just quickly kind of show how we're going to see that. So I actually put in two graphs. This is the first one, which is going to look like a parabola when you graph this. And then in Y2, I just, because I want to know where it intersects the 0.1 or the negative 0.1. Okay, I want to know where it intersects that, because those are going to be the x coordinates that puts me between that tolerance of 0.1. That's the amount of error that I can have. Okay, so if we look at that here, so I graphed, so this is my tangent line here, and then this is the actual function. And I want the difference between those two to be within this negative 0.1, because again, I know that this is going to be the smaller, and that's going to be the larger numbers there. Okay, so when I graph those, what I'm interested in is where these things intersect, and so Desmos works pretty good. I'm going to just tap here, and so if we touch these points here, 3.684, and it shows the intersection point there, and then the other one is 4.316. Okay, so I have those written down, but that's how you could go through, and Desmos is nice for this, and set that up and then see where they would intersect. Okay, and so let's go back to what we had here. So that's what I'm saying here. This is where they intersect, but they kind of were interested in, instead of the just the whole number piece, they're saying, okay, so if we're going from 4, the difference from 4, how far to the left and to the right from 4, and so 4 plus h, I'm setting that equal to each of these values, and then so h would be 3.16 or negative 3.16, so your h values for this would have a tolerance from negative 0.316 to positive 3.16. Or 0.316, sorry, and that's going to give us that amount of error in the function of that 0.1 is the amount of error that we would have. Okay, but as far as the left to right movement, you could move this far to have that amount of error in your output of your function values on the line versus on the actual function. Okay, so that's it. That's a little introduction to some linear approximation.